Today we're going to talk about stars. So in the previous module, we looked at the Big Bang theory, and the Big Bang, remember, is the theory that the universe started out with all matter in one tiny little spot, and that all that matter rapidly expanded, and then for reasons we don't really know, but then got to a certain point where that expansion kind of took over and it went at an uncontrolled rate, and it kind of threw matter all over the universe. And in some areas, that matter started to collect into this kind of clouds. And so we've got this matter, we've got dust and elements and all these things that are kind of swirling around. And that's what's called a stellar nebula. An area where that gas and dust kind of condenses into one spot is where we have the birthplace of stars. So on your handout today, what you have is the life cycle of a low mass star and a high mass star. And there are some of those stages that are the same for a low mass and a high mass, and then we have an area where it branches off. So in our chart here that's on the screen, we have one more place that we're going to talk about on the low mass side. We're going to talk about a black dwarf. Also, that's not on here. But the beginning parts of the life cycles are pretty much the same. I want you to notice on this chart that there's two different nebulas that are on here. We have a stellar nebula and we have a planetary nebula. The stellar nebula is that nursery or that birthplace of stars. The planetary nebula happens during the life cycle of the star. So there are two different things, and we'll get to that a little bit more when we talk about the planetary nebula. But we're going to start out with the stellar nebula where our stars are born. And so once again, it's that area where the gas and dust kind of concentrate, and when that happens, gravity starts to pull the particles even closer together. And because they're getting pulled closer together, there's friction that's occurring. So just like when you rub your hands and you create heat by rubbing your hands together, the same thing happens with the particles in the nebula. And so the heat that's generated in the stellar nebula is because those particles are all pushing together, they're rubbing against one another, causing friction, and that causes heat to be generated. At this point, it's not a star yet, and it's not burning anything. That heat just comes from the compression of the molecules. If we get the area to condense down into a small enough spot, we'll get a protostar. But it's not necessarily the whole nebula that's condensing down to make one protostar. If you look up at Orion in the night sky where Orion's belt is at, what you'll see if you look through a telescope is you can actually see Orion's nebula. And that particular nebula has generated lots of stars. So nebulas tend to be a really large area, and you can have lots of stars that are created out of that one spot. So when it condenses enough into an area, we tend to get a ball-shaped object with a disk around it, and that becomes our protostar. Protostar, once again, is still not burning anything. The protostar's energy is coming from gravity. It's coming from all the gravitational pull that's pulling in all these particles together, and the pressure and the gravity are causing heat to be generated. So nothing is getting burned yet. Eventually, those hydrogen atoms that are within the cloud are going to get pressed together with enough force that they're going to fuse. And once that fusion process starts, now we have a star. So protostar is before it's a star, so no fusion is happening. Once fusion starts happening in the core of the object, it becomes a star. The first step for both kinds of stars, both low mass and high mass stars, is the main sequence. So they become a star. They were in the nebula, they became a protostar, and now fusion is happening, and now we have a main sequence star. Low mass stars are just the smaller mass stars on the main sequence. The high mass stars, it's about their size and about how much matter they have. The high mass stars are bigger, and so how long they remain on the main sequence is based on their size. The low mass stars aren't going to be burning up their hydrogen as fast, and so they're going to stay longer on the main sequence than a high mass star will. The smaller stars can actually be a lot older than our bigger stars, because the bigger stars, because they're so much bigger, there's so much more gravity that's pulling in on them, that's causing that fusion to go at a greater rate, and so our bigger stars don't spend as much time on the main sequence. They all spend about 90% or so of their life on the main sequence. It's just the life of a low mass star is a lot longer than the life of a high mass star. So when they start to run out of hydrogen, they're fusing all their hydrogen. When they fuse, the two hydrogen atoms fuse together and become helium. When they run out of hydrogen to burn, that's when they're going to start to move off of the main sequence and into their next stage of the life cycle, which is either a red giant or a supergiant, depending upon their size. So we're going to talk about a low mass star first and what happens to it. So you start to have, when the helium starts to burn, there's not as much heat that's available, and so we don't have as much heat being generated, which means that our stars cool as they become a red giant or a supergiant, but they also expand because gravity's not holding them all together as much as it used to, because there's not as much heat that's being generated. And so the star will start to expand first, okay, because the helium is starting to burn. So on the side here it says the star is shrinking. That's when the star is shrinking, when it's still burning the hydrogen. When it runs out of hydrogen and starting to burn helium, now it's going to expand and it's going to get bigger. So we've come off of the main sequence, we became a red giant. The red giant, when it starts to, when it's burning through, it's starting to run out of helium to burn, now it's really starting to lose some temperature and some heat, and it really can't hold its shape anymore. And that's where we get a planetary nebula. Planetary nebula becomes a ring around the outside of the star, and it's basically the gases that the star couldn't hold onto anymore. And then we'll talk about the white dwarf and the black dwarf here in just a second. So here's our, going back to our red giant. Okay, so we had our main sequence where it was fusing helium or hydrogen into helium, and then we have our red giant, where now it's fusing helium into carbon. It does fuse a few other things as well, but primarily it's making carbon. It does make some other heavier elements, but it's not making metals at this point. Right now we're just primarily making carbon. And then, like I said, so here in the middle is the next stage of our development. So here's the planetary nebula all the way around. This is called the Cat Eye Nebula. Or I'm sorry, this one's called the Helix Nebula. And here where this red disk here is in the middle, and there's the white dot in the middle, that's the white dwarf. So the star used to be a lot bigger than that, but all of this stuff came off of the star. Now, can some of that go and become part of the stellar nebula? Absolutely, because it's all stardust, basically. But for right now, when we look at our stellar nebula, that's where the star is born. The planetary nebula is happening during the death of a star. It releases those particles back into the galaxy. So once again, here's another one. This is called the, oh, I'm sorry, this one was the Cat Eye. This one's the Helix. This is the Helix Nebula, and here's our white dwarf that's here in the middle. Here's its planetary nebula, all the gases that it's shut off, and it turns into a white dwarf. Now, the white dwarf is burning carbon, and so now this one's really hot. The temperature goes up now when we're burning carbon in the white dwarf, but there's just not as much of it, and it's going to burn it until it runs out of carbon to burn. Now, here on Earth, when we put carbon under a lot of heat and pressure, we get diamonds. And so as the white dwarf burns out and becomes a black dwarf, which is where all the fusion has stopped, astronomers hypothesize that in the middle of a black dwarf it's actually like a diamond, because that carbon has all been put under significant heat and pressure. And that's what happens when you do that with carbon. If we're a big star, we're on the main sequence and we're just a lot bigger. The next step in development is a red giant, and then it's going to explode. So the low mass stars don't explode, they just kind of fade away, but the big mass stars, they go out with a bang. And then depending on the size of the star, it's going to tell us what's going to happen to it afterwards, whether it's going to become a neutron star or a black hole. So our supergiants can come in different colors. This one's a blue supergiant. We can have red supergiants. And they started out with more mass when they collected more stuff, basically, in the stellar nebula. And so remember, they burn through their hydrogen a lot faster. They're going to burn through their helium a lot faster. They're going to expand like this and get really big. They're not as hot anymore. Their temperature goes down, but their size definitely increases. When they run out of their helium and start burning carbon, the balance just isn't there. Like in the low mass star, we could start burning carbon, we could be that white dwarf, and it was okay. But in the high mass star, there's just too much stuff. There's still much gravity that's going on, and they just can't stay there, and they're going to go supernova. And the supernova is just a giant explosion that rocks the star, It's going to push out matter all over the place. It's going to go back into stellar nebulas, and that becomes more stardust. This is called the string of pearls. This is an image from the Hubble telescope, and they hypothesize that these rings of matter out here were actually ejected about 20,000 years before the supernova explosion, which is what you can see here. This ring right here is from the supernova explosion, and this is what's left of the supergiant that's inside of there. Depending on the size of the giant, we'll either get a black hole or we'll get a neutron star. So if the mass was 3 times greater than the sun, we have a black hole, and that's where no light can escape. It just becomes this area that's pulling, there's just intense gravitational pull. It's pulling everything into it. Light doesn't escape from it. We haven't found really what we can see. We know they're there because we can see things being pulled towards them, but you can't actually take an image of a black hole because no light escapes. And when we take an image of something, we're taking an image of light, usually that comes out of something. So the black hole is one thing that could happen, and the ones that are really big, the 8 times the size of our sun, become a neutron star. Or I'm sorry, the smaller ones become neutron stars. Neutron stars are super dense. They're way denser than the white dwarf was. All that matter blows up and then it contracts right back in on itself, and becomes this really dense area of matter within our solar system, or within our universe. So that supernova is what makes our metals. Because the violence of the explosion, it can cause the elements to fuse within it, and that's how we get some of our heavier metals, is through a supernova explosion. So our sun is a low mass star, or a medium star. We're kind of right in the middle, because we used our sun as a basis to describe all other stars. And so our star will actually become a red giant. Our star is about halfway through its life on the main sequence. So if you're concerned about our star doing something crazy, we've got about 5 billion years of life left on our star. So we're good. And so are all of the people you'll ever know, and their grandchildren and great-grandchildren. But eventually it will become a red giant. When it does that, it'll take out all the inner planets when it expands in size. So we'll all become, all the way up until Mars, will become part of the sun, and really the outer planets won't be recognizable anymore, because there will be more gravitational pull, and it'll change their orbits as well. So then it'll become white dwarf after that, and then a black dwarf, and fade away. So our sun is not a explosive type star.